Okay, now we will go to the introduction. First of all, what is Simpson rule? Simpson rule is a numerical method used to approximate the definite integral of a function. It provides an efficient way to estimate the area under a curve when the exact integral is difficult or impossible to solve analytically. Why must we use Simpson rule? First of all, it's simple to implement for many functions. And second one, it provides more accurate result compared to other methods such as trapezoidal rule, especially for smooth curve. And lastly, it widely used in engineering, physics, and mathematics.
Next, I will explain about the theory of Simpson's rule. The theory of Simpson's rule is based on approximating the area under a curve by using quadratic polynomials, or as known as parabolas. This method assumes that over a small sections of the curve, a parabola can closely match the shape of the curve. Imagine you have a wiggly curvy line like a roller coaster track and you want to figure out the area underneath it. But the curve is hard to measure exactly. Instead of trying to measure the whole curve, we use parabolas, which is the smooth U-shaped curves, to fit the curve. A parabola is like a curve that can bend smoothly, and it is better at matching the shape of the curve than using straight lines. So instead of drawing straight lines over the curve, which will not follow the shape well, we draw smooth U-shaped parabolas. These parabolas fit the curve much better. Then I will explain about how the theory works. First thing first, we divide the area into sections. We chop the area into small sections like slices of a cake. Each section gets its own little parabola. These sections have to be an even number like 2, 4, or 6. Then we fit the parabola to each section. For each small section, we draw a parabola that goes through 3 points, which is the start of the section, the middle, and the end. Then we need to add them up. Once you have done for all the small sections, you need to add up the areas of all the parabolas. This gives you an approximation of the total area under the whole curve. When do we use the Simpson's rule? We use the Simpson's rule when the function is too complex to integrate by hand or with standard methods. Then we use the Simpson's rule when the curve is smooth, with no sharp turns or breaks. And lastly, we use Simpson's rule when the high accuracy is needed. Next, my other group members will explain about the whole formula of Simpson's rule in order to solve questions. Then you will be more understand on how it works.
So this is like the formula for Simpson rule, which is the 1 per 3 rule. And we will count the area of the graph. So the formula is started with the integral of functions from a to b, which is approximately equal to the width of the interval, which is h, divided by 3 and multiplied by y first, plus 4y multiplied by the summation of odd y, and then plus by 2y, which is the summation of even y, plus the last y. So this is the second formula, which is the 3 per 8 rule. So the formula is started with the integral of functions from a to b, which is approximately equal to 3 times the width of the interval, which is h per 8, and multiplied by the first y plus 3 multiplied by second y, then plus 3 multiplied by the third y, and lastly plus the last y.
Jot down or list down everything, the information you have been given. So which is already wrote it down for we all to see. N equal to x, and B is the maximum value or the top interrogation value. So B equal to 2.0, and A is the below value, which is the minimum value, which is A equal to 1.2. So first thing is we have to find the H. H is actually the size of each value for x. So H equal to B minus A divided, the total of that will be divided by n. So just put it in the formula. So 2.0 minus 1.2 equals 0.8, and 0.8 divided by 8. So we got H equals 0.1. So after we got H, what do we have to do? So quickly, just do a table. X from 1.2 to 2.0 from A until B. How to decide for the each size and how much is depending on your H and N. The size of it will be H, which is 0.1. That's why you see it's 1.2, and then the next one is 1.3, next one 1.4. It's just increment of 0.1. So we assign from 0 to 8. So you will see at the table, it is equal to n. So it actually have to be the same size. Okay. So from the x value, you just put it into the formula, into the question given, and then you get the y value because you already get the x value. So in order to get the y value, you substitute the x value with each one x value that you get, and then you get the y value for each x value that you substitute in. So it will be 0.1 divided by 3 times 1.652, the first value, plus 3, the last value, plus 4, then this 4 will be multiplied by the first column of y value, third column of the y value, fifth column of the y value, and the seventh column of the y value, sum it together and multiply by 4, plus 2, and the sum of the even number which we don't use it. Okay, we have not used it. So the y value in the second column, which is 1.935, and the fourth column 2.257, and the last but not least is the sixth column, which is 2.614. So you guys will get the answer 1.824y. For the question, you must have 3 decimal places. You can write it as 1.824. So that's how you do it. So there you go. So basically it's kind of easy if you get the idea and jot down everything that you have, so you guys can understand clearly. So you guys actually the jot down thing, the information and the table is very crucial in order for you to see and do it correctly, so you don't miss out anything. So for this is one of the example question and an example answer from me. So you guys can try it on your own. Try the formula. Just remember the formula and try it. Implication it. So I hope you all the best. Okay.
Simpson rules is a powerful numerical integration technique designed to approximate definite integrals with high accuracy by dividing area under a curve into even section and fitting parabola to each. The method efficiently estimates the total area, making it particularly useful for smooth curves. This technique is simpler to implement than many alternatives and provides more precise results than the trapezoidal rule. Commonly applied in engineering, physics, and applied mathematics, Simpson's rules is most effective for functions too complex to integrate analytically, ensuring robust solutions for practical problems.